David Koerner, the evolving link between music and science. Dr. David Koerner is an emeritus associate professor of astronomy and planetary science at Northern Arizona University. His work has focused on star and planet formation, astrobiology, and indigenous astronomy at Caltech, JPL, University of Pennsylvania, and NAU. Dr. Koerner is also an accomplished musician with an MM in instrumental performance and is completing the graduate certificate in piano performance at NAU. He plays violin with Dark Sky Quartet, viola with Flagstaff Symphony, and recently performed Beethoven's Emperor Piano Concerto with Orchestra Northern Arizona. So please give a very warm welcome for Dr. Koerner.
Thank you, Catherine. Well, welcome everybody. This is kind of a challenging subject. I was asked to speak on it by some people involved both in the festival and with Flagstaff Symphony. And I think partly because of the upcoming concert, I'll refer to it again later on tomorrow night, of Flagstaff Symphony, has a little bit of this intersection. There will be a piano concerto on the planets. And we'll talk about that a little bit later. So what do these two things have to do with each other? Music and science, or in my case, music and astronomy. Every time I hear that question, I think of an applied physics professor I know who, when asked by a student to lead a student group in philosophy of physics, two other disparate subjects, replied to him tartly and said, "What do physics and philosophy have to do with each other?" And the student thought and said some things, and the applied physicist just said, "Nothing." Well, I thought that was a little too sarcastic, so I was the faculty advisor for that group. I think there's a point to that, in that these things have a lot of differences between them that ought not to be ignored. But at the same time, there's been a hand-in-hand partnership between music and astronomy in particular for 3,000 years. Yeah. And it's changed. It's not the same now as it was 3,000 years ago. So that's why I refer to it as an evolving relationship, because it's not the same now as it was. So I'm going to start off and first talk a little bit about the beginning of music, and especially astronomy, in the Greek period and through the medieval period as a kind of historical context. I'm sure, have you all heard the phrase music of the spheres? What does that mean? Well, that's what we're gonna talk about. What does that really mean? Okay. So it goes back to Pythagoras, but anything that goes to Pythagoras probably goes back further than that, because Pythagoras, though he's credited with a lot of things, learned a lot from the Babylonians going back even 1,000 years before him. Case in point, we're all familiar with the Pythagorean Theorem, and Pythagoras must have discovered that, right? No, he did not. It appears in Babylonian cuneiform tablets 1,000 years before Pythagoras even lived. So let that be a lesson to you. But another thing he's credited with is this idea of the music of the spheres. And he was a big champion of the idea that the universe is mathematical, and so is music. And so really a lot of his perspective has to do with describing the universe mathematically. Now, his mathematics were not the same as ours today, but they were kind of in the beginning. And where did he get this idea, this association of math and music? Really, for him, it's more an association of math and sound. And here's a couple things experiments he worked on. This is just a lyre here, right? But it's a stringed instrument. So people were used to plucking strings, and they figured out that the pitches of the strings were proportional to, if you had the same tension on the string, they were proportional to the length of the string. And so they actually had this funny little experimental device called the Mono Chord. And all it is a string. And you have a weight on one side that will keep the tension in the string constant. And then by moving these little kind of bridges, it's like a bridge on a string instrument on B and C, you could change the length of this string, but the tension would stay constant. And so then you could pick out pitches, and you can see how those pitches change with the length of the string that you are plucking. And when he did this, he found some interesting things. What he discovered is if you cut it exactly in half, you'll have these two pitches of a very consonant sound, which we call an octave, if you know what an octave is, and so that formed, he thought, wow, this is a relationship of 1 to 2. They have an integer relationship, an integer ratio, 1 to 2. And he loved integers. So Pythagoras believed that that numbers were integers, and that was it. Pi, that other stuff, those weren't numbers. They were things, they were geometric things, but they weren't numbers to Pythagoras, okay? So this relationship of integers was a big deal to him. So he found the octave when the string lengths differed by a factor of 2. Then if you take a string that's half, and then you compare it to a string length of a third, you get another very pure sounding interval, the fifth. If you hear like medieval music and chant, and you'll hear singers sing in parallel fifths, it's very characteristic of a kind of Gothic time, but it's very resonant. And that's the thing when they have these relationships. And it goes on up from there. If you have intervals of a third to a fourth, you get the interval of fourth. And those first 3 intervals to Pythagoras, the octave, the fifth, and the fourth, were what he called the consonant intervals, the most pleasing intervals. They were the most reverberant. As you go up higher along these ratios, you can get smaller and smaller intervals. And then the problem in music theory is to develop a scale out of the small intervals. I say the problem because if you stack things this way, your scales will not add up to perfect octaves as you go on up the scale. You have to fudge to make that happen. And that's the scale we're comfortable with today, the so-called well-tempered scale on the piano. It doesn't obey all these for the smaller intervals. Okay, now a lot of these are built on the vibrational modes of a string. If you have a string here, if it's vibrating all the way across the length of the string, it gives you a fundamental tone. It may also simultaneously vibrate in halves, and that gives you the octave above. And usually when you play a string, all of these are vibrating at once. You don't necessarily notice because you hear the fundamental very powerfully, but the timbre of the pitch that you hear has to do with how many of these other higher modes are vibrating. All right. Now to Pythagoras, they were big on things like squaring the circle, finding the diagonal in a square. As you know right away, that immediately involves you in irrational numbers. And those are not, but they're not numbers to Pythagoras. What does he do? So he considers them to be some sort of geometric entities. And they were, when you go then to try to build up an idea of the cosmos, you're faced with geometry, right away. So you're going to have this idea of irrational numbers. On the other hand, for him, music was these consonant tones in their relationship, which were relationships of integers. And that was arithmetic. So arithmetic was related to music, geometry was related to astronomy, and they're all together in some sort of mathematical soup. And those 4 subjects then became the thing, one of the big things you had to study. And it continued to be so all the way into medieval times. To understand the cosmos and the universe, the other 3, right, were like rhetoric and logic and stuff like that. But these it was geometry, arithmetic, music, and Astronomy. Oh yeah, the field I'm in. I forgot. Anyway. And of course, later on, you've probably heard the term for these four. Anybody know what it is? The Quadrivium. Oh, I gave it away. But that was a word that was invented not until like the 6th century with Neo-Pythagoreans, just to describe what Pythagoras was talking about. Okay, so these all went together. So you see, music and astronomy are together for these mathematical reasons. And how did they work in Pythagoras's cosmology? Pythagoras believed that the planets, in particular celestial bodies, were moving on circular orbits around the Earth. And moreover, he believed that their distances from Earth gave them a particular pitch, a sound, kind of like on the Mono Chord, right? The length of the string. So their distances were singing this tone. Can you hear it? Me neither. So, but so there were theories about that. Why don't you hear this? And one was, well, it's always been playing, so you can't distinguish it. It's there. If it stopped, you would notice. But since it's always been there, you don't pick it up. That was one theory. The other one I like even better, only Pythagoras could hear it because he had special powers. The volume of this sound was proportional to the speed of the planets, and the pitch was proportional to their distance. And because the universe has to be harmonious, the distances of the planets relative to each other had to occur in these integer relationships so that they would be consonant relationships. So imagine this beautiful picture, and this is the music of the spheres from Greek times, that all these planets have a particular tone due to their distance, and they make some gorgeous chord that's perfectly harmonious. And as they go around in their orbits, it's just the whole solar system is singing away, right? That's the music of the spheres. The spheres, you know, we're used to seeing planets as spheres, so you might think it's the sphere of a planet, but it's actually the idea that the planets were embedded in crystalline spheres, big spheres, and the spheres were moving, and those are the spheres that were making the music. Okay, so that's how Pythagoras got started. Now it's interesting. You might think that didn't last very long. It lasted a really, really long time, and it motivated actually things in post-Copernican times. And that's what we're going to see. And this blew me away to find it out. So move on ahead, and we have Ptolemy, an astronomer in Egypt in like the 1st or 2nd century, still going under the same principles as Pythagoras, but now he has to solve this problem. And it's this problem when you look at the planets and when they're in opposition, they tend to go backwards against the background stars for a little bit and then they go back. A condition we all know as retrograde. Uh-oh. Mercury's in retrograde. You're in trouble. Okay. Well, Ptolemy, to his credit, was trying to just find a mathematical setup which would produce that apparent motion against the sky. And to do it, he had these little circles on circles called epicycles. And that's the way he viewed it. And of course, they're all centered on Earth. So the planet could temporarily go backwards in an epicycle, and that would work. The reason I bring this up is because what do you think this would do to the music of the spheres? If the music depends on the distance from the Earth, and then suddenly the distance changes, the pitch has to change. And in fact, that's the way Ptolemy thought of it. The scales would have to change, and there would be temporarily a different note in the scale. And this was compared to different modes of scales, and that's how he understood it. Now, Ptolemy himself believed in this music association so much that he wrote a whole separate acoustic treatise, Harmonics. He wrote a musical treatise, not just his astronomy, right? And we'll find that happens later. That's how much this was still moving together. I'm talking too slow, so I have to keep going. But here's the idea of different scales that have these different modes in them. If you're a music major, in music theory, you have to learn all these different modes. Ionian, Lydian, Mixolydian. The two that we hear most in modern popular music are the major scale, which is Ionian, and the minor scale, which is Aeolian. But we often hear these slight variations as well. And in Ptolemy's time, these were compared to the way the scale changed when planets went into retrograde motion. No key about what exactly scale you get when Mercury goes into retrograde. It must have been awful. I don't know. All right, so I'm going to skip way ahead. There's other interesting characters in there that develop this idea of music and the music of the spheres. But when you get to Copernicus, now you change the whole arrangement. Things are not moving around the Earth, they're moving around the sun. So you'd think this would just break apart this old idea. Oh no. You simply then can change it and say the tones have to do with the distance between the planet and the sun, right? And so that's what they did. And the interesting thing is retrograde motion goes away as a change in distance. It's just when the Earth laps a planet, right? And so you don't have to have these special modes. It kind of simplifies things. So here's Copernicus, and he had his heliocentric model. The Earth rotates and moves around the sun. Planets move around the sun on circular orbits. The stars are just totally far away, and they don't really move. And the moon goes around the Earth. You guys all know about this. And that naturally produces retrograde motion. I have this slide. I'm not going to go into detail to it. It's from an intro astronomy class, but it simply illustrates how when the Earth laps, say Mars, along here, it looks against the background stars like Mars, makes a little backward loop, and that's retrograde motion. All right, this brings us to the peak of music of the spheres ideas with Johannes Kepler. Now, the problem with Copernicus's view was that even though it was a simpler idea, it was starting to fail to predict the positions of the planets exactly. So how can you fix it? And the first thing people did was, well, let's go back to epicycles. So they started throwing in epicycles. By Kepler's time, it was just about as complicated as Ptolemy's. And so it wasn't really simpler. I mean, what can you do? And the problem was they were stuck on the idea of circular planetary orbits. And of course, as we know, that's not how things are. And Kepler was the guy who first found it out. He was an assistant to Tycho Brahe, who died suddenly. People thought maybe poisoning. People thought maybe even Kepler did it at some point. True story, they exhumed Tycho Brahe a few years ago to do a 500-year later autopsy and see if he was really poisoned. The answer is no. And so the going theory, which should be a warning to everyone in this room throughout this talk, the going theory is that he died because he couldn't go to the bathroom while he was in an occasion of royalty. And his bladder burst. True story. So that stood. People wanted it to not be having to go to the bathroom. They wanted it to be poisoning. He was a character who had his nose shot off in a duel, had an assembly of several different noses that he then wore afterwards. But Kepler was his assistant and had all this great data on Mars. So Kepler was also a very good mathematician. And Kepler was a true believer in music of the spheres. So how did he resolve this? And I don't know when his aha moment was. He read Ptolemy's harmonics. So he was used to Ptolemy's idea of different modes, changing the scale a little bit if you need to accommodate these revisions to the theory. And Kepler himself wrote a harmony of the world with a lot of this musical acoustics and all this kind of stuff. You don't usually talk about it in intro astronomy or science philosophy courses, but it was definitely there. It was a huge factor. And ultimately, Kepler derived 3 laws of planetary motion that then were interpreted by Newton to come up with his powerful gravitational theory that explained it all for you. And his laws of motion included things like the number one big thing: the orbits of the planets are ellipses. They're not circles. What's an ellipse? It's kind of oval-like, right? So its distance changes as it goes around, right? So what does this do to the music of the spheres? And did Kepler try to retain this? Short answer is yes, he did. This is the idea that here is this ellipse. It's exaggerated, but the planet has a changing distance. And the amount by which this orbit is kind of squashed and deviates from circle is mathematically known as the eccentricity. So the more eccentric the orbit is, the more the distance changes between the planet and the sun, right? If you had an eccentricity of 0, it'd be a circle. So Kepler compared this to more complex musical theory of the day, including a lot of the polyphony that was going on in his time. He was a big fan of de Lassus, for example, an amazing choral composer of the day. And composition in Kepler's time was beginning to become much more polyphonic, meaning you would have a lot more variation between the voices. Like you go back 600 years from Kepler and you've got chant and everybody's singing the same note. All right, get on with it, right? Gradually, people had different parts and their notes would change and weave in between, and people appreciated the beauty of it. Of course, there were theological debates over it. At one point, they wanted to outlaw it in the Catholic Church because it was just too, whatever. But it survived. And he compared then this polyphony to the tones that would result from these elliptic motions. As an aside, his second and third laws had to do with how fast the planets go in these elliptical orbits. We don't need to go into too much detail about it. But let's go back to the eccentricity. So here he had good enough observations that he could come up with something close to what we know today. If you look in the table at right, you can see how the eccentricities change for the different planets. Some are much more eccentric than others. Mercury is pretty out there. Yeah, Pluto, well, Pluto shouldn't even be on there. No, I can't say that. I can't say that in this room. Pluto is exceptional, as you can see. Let's see, take a look. Who else is pretty eccentric? Venus is pretty circular, isn't it? But another one that's pretty good is Mars. Mars is pretty eccentric, and I think that's why Tycho Brahe's Mars data was so helpful for Kepler to discover the elliptical orbits of planets, because it is fairly elliptical. All right, so you can see the magnitude of the ellipticity. But here is a little figure taken from Kepler's writings of his representation of the ellipticity of planets. And this blows me away. What is going on here? You can see scales of various ranges, and the range of notes is proportional to the eccentricity, because the amount that the tone would change as you go from nearby to short would be proportional to these to the distance it is from the sun. And so this is Kepler, still music of the spheres in the 17th century, a few decades before Newton. Now, the only thing that's wrong with this is that they're discretized. It's as if the planet sits here and then jumps again. We know that doesn't happen. So these scales would have to be played with something like a slide guitar, right? They would have, because the orbit is really continuously going, you know, this planet, they sound like a really slow siren. Music of the spheres. All right, so that in brief, we come up to the period where the Pythagorean version of music of the spheres is about to go by the wayside, because the next thing that happens, Newton comes up with a mathematical formulation, and nobody's, you know, Pythagoras is dead, so nobody can hear this. Nobody can hear these tones anywhere, so you'd think they're starting to get skeptical. Yes, they should be. About this time, Galileo starts to study sound, and Galileo comes from a musical family, as so many scientists do. His father was a big leader in Italian opera. His brother was a lutenist. Galileo certainly played lute himself, and so he experimented with everything he did. So he was really looking at how do these strings make sound, right? And he came up with the idea that it's the vibrations, the frequency of the vibrations in the string that determine the pitch. And that's something people hadn't really gotten for all this time. They just had some kind of weird mystical idea about how music is generated. They thought of music as a thing that just left whatever instrument you were using and came out and reached you, just, you know, whether it was from the planets or whatever. And of course, Galileo understood that these strings were vibrating, and it wasn't long before some experiments were done, and it was understood that the vibrations are pushing and pulling the air and making waves in the air. So sound is a pressure wave in the air that comes to your ear, which can then pick it up in sympathetic vibrations. That doesn't bode well for music of the spheres. You know, in space, no one can hear you scream, right? Nor can they hear Pythagorean tones. All right, so there's so much that then went on in the 18th and 19th century, and I'm not going to talk about it, but it had to do with gradual discoveries of wave physics. Sound was a wave, and that discovery was used to propel new insight about other waves. Light waves in particular, electromagnetic waves in general. Of course, electromagnetic waves covers a lot of things, covers radio waves, a lot of things in the spectrum, infrared, ultraviolet, etc. And much later on, we found in quantum mechanics, the wave-like nature of particles. And also more recently, Einstein's theory of relativity, general theory of relativity, predicted that space-time would wave in something called gravity waves. So now you've got, in the 19th and 20th centuries, this idea of wave physics is much more sophisticated. But has it anything to do with music? That's a rhetorical question that we could just drop everything for an hour, right? Of course, it's got some big philosophy. What is music? And, you know, I don't know. It's different things to different people, right? Is there a difference between music and just any sound? Depends on the listener, right? So that's a philosophical sort of classical argument that we don't need to get into right now, but it's going to appear, as you'll see. One thing, I forgot I have to do a plug here before. If you want to know more about this, this is the book. Peter Pesich, Music and the Emergence of Modern Science. And he was a very good physicist and a very accomplished pianist and violinist. And he traces especially the stuff that I'm skipping, as well as the earlier stuff. So the 18th and 19th centuries, wow, it's amazing how much music influenced the development of all the physics in those times. And I'm not going to talk about it, but he does, and does it very well. So for further knowledge, okay, let's see. All right, so this idea, which when I get to these videos, we're going to talk about modern ideas of sonification. Basically, it comes down to the idea that waves can be transported in different media, and if we are careful about how we transform them from one media into another, they can carry the same information. And of course, this is how we carry on a lot of our lives, right? You know, ever since radio waves were sent and then turned into sound waves in a speaker so that you could send information back and go from an electromagnetic wave to an acoustic wave. So here's the thing. We all the time transfer music from an acoustic signal and media to an electronic or a digital signal and a media, and then back again. So what this means is it opens up the possibility that maybe there are things going on in the electromagnetic realm that if we just took them out and transformed them into acoustics, they would be interesting. And it might be very interesting to us because as humans who evolved this sense of hearing, our sense of hearing is very different from our sense of seeing, both emotionally and in many different ways. And so when we grasp something because we've heard it, it's kind of a different perception of it. And so this is, I think, behind what's been going on with the idea of sonification. And what sonification basically means taking data that may be wave related or whatever, and turning it into sound, the same way you would take an electronic impulse that is of music and then play it through a speaker. So that's what's meant by sonification. So without further ado, I'm going to start into playing you a litany of examples, because that's the fun stuff. All right. The first thing I want to play is sonification of signals from pulsars. What's a pulsar? So a pulsar, if you have a very big, massive star, doesn't live long, blows up, what's left afterwards, if it's a particular mass to start with, is a neutron star. The neutron star collapses, it's solid neutrons, it's ridiculously massive, it's several solar masses with a diameter of what, 10 or 12 miles. That's ridiculous. And it is spinning really fast. And as it spins, its magnetic field rotates with it, and it throws out a radio signal. Now, this is a pretty simple thing. It just throws out a kind of beep. And of course, the first pulsar that was discovered was just these series of beeps, which no one knew what it was. And they thought, aliens, because that's what we always think. And it was even called the little green man signal for quite a while. It took quite a while for theorists to catch up and say, look, this could be a neutron star, or what we call a pulsar. True enough, it was. I'll say, what's this? This is a supernova from 1,000 years ago. So you can see all the gas that was thrown off. And in the middle of it is a pulsar. And here's a schematic of a pulsar. This big, well, it's not big, it's small, relatively speaking. And it has magnetic field lines, and it's beaming out at the poles. And as it rotates, we get a little fraction of its beam. And how fast do you think it rotates? I mean, it's like, it's 10, 12 miles across. How long does it take that to go around? When these things first have collapsed, they have so much angular momentum that they go thousands of times a second. Just can't imagine that. Now, gradually, through magnetic braking, they slow down. And then if they've been out there a long time, it might be a whole second to go around. Whoa. But the young ones, sometimes called millisecond pulsars, are really good. Okay, so we get this in the radio, this little beep. It's not aliens, but we can turn it into sound and we can listen to it. And what do you think it sounds like? I'm playing this one first because it's kind of the simplest, straightforward one. And hopefully the sound will come through. And the crab is one of them on here. That's a slow one. So there's the crab. It's only 1,000 years old. Okay, is that music? I know some percussionists who would say yes. And they would be very impressed because no way can they play that. Okay. Another thing that's been sonified, if you will, is kind of an exciting discovery. And waves travel in space-time if some very massive gravitational event has happened. And we've learned to detect them with LIGO, an interferometer, and it's a very sensitive observation, very hard to detect. But the two events that I'm going to play that we have detected are the mergers of black holes. So you have a binary star system, both of them blow up and end up with black holes. The black holes are rotating against each other and they eventually spiral in and wham, that's a tremor in the force, right? And we can detect it zillions of light years away. And people have sonified it and put out press release headlines about it being the music of the spheres. Of course, it's not the same, right? But let's take a look at it. It's I don't know what you'll think about it because it's just the merger happens and that's it. And you can transpose it up a little. There you have it, the music of black hole mergers. All right, now this starts to get into something that sounds a little bit more like music. And it's a group from the Chandra X-ray satellite team, which has gone about the process of turning images into music. And I'll let the introduction here explain how they do that. And then you'll see some of their turning several images into music. So I'll just let the intro do the explaining.
The center of our Milky Way galaxy is too distant for us to visit. but we can still explore it. Telescopes give us a chance to see what the galactic center looks like in different types of light. By translating the inherently digital data captured by telescopes in space into images, astronomers create visual representations that would otherwise be invisible to us. But what about experiencing these images with other systems, like hearing? Sonification is the process that translates data into sound, and a new process brings the center and the way to listeners for the perfect time. As the bar moves from left to right, the sound represents the position and brightness of the source of light by navigating another experience. All these and physics. The light of objects located toward the top of the earth are very higher, while the intensity of the light controls the velocity. Each type of light reveals different phenomena in the CDS, which is roughly 400 light years across, at a distance of about 23,000 light years from Earth. The supermassive black hole center of the galaxy, called Sagittarius A star, resides in the bright regions to a lower radius. In addition to the galactic center, this team has also produced sonified versions of the remains of a supernova called Cassiopeia A, or Cap A. And the stories of creation, located in 1916. Sonification content like this allow different audiences, including blind and visually impaired communities, to explore space through data.
Okay, so that sounds a little bit more like music. Modern music, to be sure. Avant-garde music, perhaps, right? But it has a more an array of frequencies, et cetera. And of course, they've done it with a very specific trick of rastering and then moving across the image. So there's a few more of these. Okay, go away. There's a few more of these that I think sound very cool, so I'm just going to play them. This is a cluster of two galaxies that are colliding, the bullet cluster, and hot intergalactic gas has heated up and is radiating, and so you get kind of an interesting sound. This is a star-forming cluster, massive stars. It has pizzicato stars. And there are more examples of these that you can find on YouTube. just Google sonification, Chandra maybe, and you'll find some, and they're pretty cool. I'd like to close with one other topic of music and science, and that is the idea of using scientific principles of natural science to come up with a composition, a musical composition. And that's what's going to happen tomorrow night with the concerto on the planets. So you're probably familiar with Holst's planets because they play out all the time. It's cool music. But Holst was very interested in astrology. So his idea of the planets was to bring out their astrological significance. The composer of tomorrow night's concerto is more interested in the scientific idea. So I haven't listened to the concerto myself. I would be playing, but I injured my shoulder, so I can't bow right now. It's kind of sad. But he said, for example, in his planet Neptune, he knows there's very high winds on Neptune. And so he endeavored to portray this windiness in the music that he wrote. Now, I'm very interested in this because I like playing stuff that has a scientific program. So I have the nerve to voice on you a little thing, a project of my own. I just started taking composition over at NAU, and I'm trying to write piano pieces for myself, but that have scientific allusions. And I wrote this little one I want to play on the star Altair. If you go out in the summer and you see the big summer triangle, 3 stars, the one most south is Altair. Altair is a 1.2 billion year old A star that is a very fast rotator, right? Our sun takes about 20 days to go around, Altair 9 hours. And Altair is almost twice as massive as the sun. After 1.2 billion years, Altair is starting to go into a transition where it's used up all its fuel in the core. It's going to start burning fuel in a shell, and then it's going to expand to become a giant star. So it's at this cusp of a big transition. So I wrote this piece for piano, and I tried to portray this rapid spinning. So it has this spinning motif, and a first section where the core fills up with helium, and then it has a big, it's full, and then it starts to burn in a shell and expand, and it's just starting its expansion. So see if you think the music evokes the astronomy. Thank you. Now my goal with a piece like that is to get the listener to feel the reality of that astronomical object more. A lot of science we talk about has so many facts and whatever, it just kind of goes over your head and it doesn't really register. But the things we're talking about are dramatic. They're amazing things. So tomorrow night, Flag Symphony will be playing this piano concerto, A Planet's Odyssey. And so it should be also an emotional voyage to the planets for the audience. And you're all invited to go hear that. I think that's my last slide. Oh, I'm supposed to tell you all to fill out a survey, www.scifest.org. And I'm also supposed to preach the virtues of our loving sponsors. And so thank you, sponsors.